Let's try another function here. Example 2, it says determining concavity. So it says determine the open intervals of which the graph of f of x equals x squared plus 1 over x squared minus 4 is concave up or concave down. Okay, excellent. So what do we have to do? Well, the first thing we have to do is find that first derivative. Find that first derivative. So let's find that first derivative. The first derivative is going to use the quotient rule. The quotient rule is low, which would be x squared minus 4, times the derivative of high. Well, the derivative of x squared plus 1 is simply 2x, minus the high, which would be x squared plus 1, times the derivative of the low. Well, the derivative of x squared minus 4 is simply 2x, all over the bottom squared, which would be x squared minus 4 quantity squared. So I'm going to clean this up a little bit. I'm going to distribute out my 2x. So 2x times x squared would be 2x cubed. 2x times negative 4 would be minus 8x. I'm going to distribute my negative and the 2x. Be very careful with distributing the negative in this. Negative 2x times x squared would be minus 2x cubed. And negative 2x times 1 would be a minus 2x. This is all over x squared minus 4 quantity squared. Notice in the numerator the 2x is cubed. We combine like terms, so I'm getting a derivative of minus 8x minus 2x would be a minus 10x all over x squared minus 4 quantity squared. Again, this wants to know the intervals of concavity. Concavity tells me I need to look at the second derivative of the function. So this isn't really the function that I care about. What I care about is the second derivative. So that's the next step, is finding the second derivative of this function. So to find the second derivative of this function, yet again, I have to use the quotient rule. Let's look at this. F double prime of x. I'm going to zoom in and concentrate on this real quick. So we're going to have the bottom function, the low function, x squared minus 4 quantity squared, times the derivative of the top. Well, the derivative of minus 10x is a minus 10. Minus the top, which would be a minus 10x, times the derivative of the bottom. This one's going to be a little more difficult because we need the chain rule. So what's the derivative of x squared minus 4 quantity squared? Well, drop the power, keep the inside just the same, so that would be 2 times x squared minus 4 to the power minus 1, so that would be the first, times the derivative of the inside. Well, the derivative of x squared minus 4 is 2x. Again, that's from the chain rule, taking the derivative of the inside. All of this is over x squared minus 4 quantity squared, but then I need to square that, right? So the bottom squared. So it's really x squared minus 4 raised to the 4th power. So let's do some math again, cleaning this up. On the first one, I'd have a negative 10 times x squared minus 4 quantity squared. The next one, I have a minus negative 10x times a 2x times a 2. So if I do that, if I do a negative negative 10, so that would be a positive 10x, times 2 would be 20x, times 2x would be 40x cubed, so plus 40x squared. Again, that's 10x times 2 is 20x, times 2x would be 40x squared. And then I still have my x squared minus 4 on that one. And this is all over x squared minus 4 squared would make it the 4th power. So what do? I realize that I have an x squared minus 4 in common up top. So if I factor out that x squared minus 4, I would have an x squared minus 4 times, well, what would be left in this first term? If I took away the x squared minus 4, I would have a minus 10 times one of the x squared minus 4's left. In the second term, if I took away the x squared minus 4, I'd be left with just the 40x squared. So that's plus 40x squared. And all of this is over x squared minus 4 raised to the 4th. Okay, let's do some simplification here. In the numerator, I have a factor of x squared minus 4. On the denominator, I have a factor of x squared minus 4, so that would turn into an x squared minus 4 cubed in the denominator. And I'm going to go ahead and do some math here in the numerator so I don't have to write another step. I'm going to do minus 10x squared plus 40. So this is really minus 10x squared plus 40 if you look at that. And now I'm going to combine like terms. So if I have a minus 10x squared plus 40x squared, I should be left with a 30x squared plus 40 on top. And then on bottom I have x squared minus 4 quantity cubed. So that should be my second derivative in simplified form. I do notice I could factor out a 10 in the numerator, but quite honestly, there's no point of doing that at this point in time. Okay, so let's look at this. What do I need to do with the second derivative? Why did I find the second derivative? Well, I need to find the points where the second derivative is equal to 0 and where the second derivative is undefined. Okay, great. When is the second derivative is 30x squared plus 40 all over x squared minus 4 quantity cubed. When is a fraction equal to 0? When its numerator equals 0. So that'd be 30x squared plus 40 equals 0. Subtract 40 from both sides, you'd have 30x squared equals negative 40. Divide both sides by 30 and you'd have x squared equals negative 40 over 30. And I notice if I take a square root of that, I'm taking a square root of a negative number, which is undefined. So that never actually happens, so I don't need to worry about that. So f double prime of x is never equal to 0. When is the second derivative undefined? Well, again, a fraction is undefined when its denominator equals 0. So this would be x squared minus 4 quantity cubed equals 0. If I cube root both sides, I'd have x squared minus 4 equals 0. Add 4 to both sides, I'd have x squared equals 4. And then remember, anytime I take a square root, I have to remember plus or minus. So I'm getting x equals negative 2, and 2 are the only points that we need to worry about. Whew, that was a lot of work, a lot of talk right in there. But all I have done is found a second derivative and then set it equal to 0 or undefined. So what do I do for my third step now? Well, for my third step, I make the interval and I plot those points. So here's my interval. The points that I determined were negative 2 and 2. I'm going to note here, if we look at this for the second derivative, it was undefined at negative 2, and it was also undefined at x equals 2. Okay? I look at my first interval. My first interval would be negative infinity to negative 2. Second interval would be negative 2 to 2. And my last interval would be 2 to infinity. So I've plotted a number line and I've determined my intervals that I need to test. That's step 3. Let's move on to step 4. Step 4 is actually test a point in each one of those intervals. Let's be careful here. What are we plugging it into? We're plugging it into the second derivative. The second derivative in this case is 30x squared plus 40 all over x squared minus 4 quantity cubed. I need a number in the first interval, so pick any number between negative infinity and negative 2. I'll pick something like negative 10. We need a number in the second interval, any number between negative 2 and 2. I'll pick the number 0. We need the third interval, any number between 2 and infinity. How about the number 10? I like using as easy numbers as possible. I'm going to do a little bit of analysis because I need to plug each one of these into the second derivative, but what I'm noticing is when I do 30x squared is always positive, times 30 is positive, plus 40 is positive. So I know no matter what number I put in, my numerator is always going to be positive, so I don't need to worry about plugging it into the numerator. Let's look now at plugging in negative 10 into the denominator. X squared would be positive minus 4, still positive, and a positive cubed is still positive. We know a positive divided by a positive is a positive. So that entire first interval, because negative 10 was the test point, was positive, that entire first interval, the second derivative must be positive. Let's plug in 0. Again, all we care about is the bottom. 0 squared minus 4 is negative, and a negative cubed is negative. So when we plugged in 0, we would have gotten a positive over a negative. A positive over a negative is negative. Because our test point in that interval was negative, that entire interval, the second derivative, must be negative. Let's look at 10. 10 squared minus 4 is a positive number. Cubed is still positive. So when we plugged in 10, we got a positive over a positive. A positive divided by a positive is positive. So when we plug in 10, the second derivative is positive. We'll go back to the chart, the number line. On the interval 2 to infinity, our test point was 10 was positive, so every point in that interval, the second derivative must be positive. Now that we've done our test point for our intervals, we are actually able to make a conclusion here. What we can do is we can look at the actual function, which is f of x. Because the second derivative is positive, I know that my function must be concave up on that interval. Because my second derivative is negative, I know I must be concave down on that interval. And the last one, second derivative is positive, so again I must be concave up on that interval. So this allows us to complete our answer. Again, where was it concave up? Well, it's concave up anytime that second derivative is positive. That was on the intervals negative infinity to negative 2 and 2 to infinity. So let's write those answers there. Negative infinity to negative 2 and also 2 to infinity. And then where's the function concave down? Well, the function is concave down when the second derivative is negative, and that was on the interval negative 2 to 2. Notice we always use open parentheses on these, never use closed parentheses, always, always, always open parentheses. Okay, let's continue reading the page. So if you notice here, we have points where it changed, the concavity changed from positive to negative and negative to positive. So what are the points when it does that? Because with the first derivative where it changed from positive to negative, that was increasing to decreasing. And the first derivative test told us it was a local or relative maximum. In any place where the derivative changed from negative to positive, that was decreasing to increasing. And again, the first derivative test told us this was a relative or local minimum. So what happens when the second derivative changes sign? Well, there's a couple of things. The first thing is that point must be in the actual domain of the function. So if we look at the previous example, we do have points where it changed from positive to negative and points where it changed from negative to positive. But what I want you to notice is this is at x equals negative 2 and 2. And if we plug that into the original function, if we did negative 2 squared minus 4, we would be dividing by 0. Same thing, 2 squared minus 4, we would be dividing by 0. So these are actually, negative 2 and 2 are not points in the domain. If they're not points in the domain, it's where it's undefined. In this case, it's where there's vertical asymptotes, which you'll learn about later or you reviewed in the review sections. Those are vertical asymptotes, but they're not defined at that point, so it's no point. So the first thing is the point must be defined there. If the point is defined there and the concavity changes, whether it be from plus to minus or from minus to plus, those are something called an inflection point. So a point of inflection is where it changes concavity. That's all a point of inflection is. A point of inflection is where it changes concavity. So it's any point where you're going from, well, let's look at this picture here. I begin with concave up, so that means my second derivative here would be positive. And then I go to concave down, so that means my second derivative would be negative. So this is from positive to negative. That point right there is called an inflection point. Okay? Looks like, let's look at the next one. Here's concave down, so that would be negative. Concave up on the second half, that would be the second derivative is positive. So here's negative to positive. Again, that is a point of inflection. Okay? Notice the slope of the tangent line at those points. Here's a slope where it's positive, here's where it's 0, and here's a slope where the actual first derivative, the slope of the tangent line's completely vertical, so that's undefined. So inflection points can happen at any first derivative value. A point of inflection can happen at any first derivative value, whether it's positive, negative, 0, or undefined. So points of inflection, it does not matter what the first derivative is doing, it matters what the second derivative is doing and the function value at that point. So it says, let f be a function that is continuous on an open interval. In other words, it is defined. Let c be a point at the interval. If the graph f has a tangent line at the point c, f of c, then this point is a point of inflection of the graph of f when the concavity of f changes from upward to downward or downward to upward at that point. So again, two things to note. The function must be defined at that point. The second part of this is f double prime of x, the second derivative, must change signs at that point. So if you meet those two conditions, first condition being it's defined, second condition being that the second derivative changes sign, then if the second derivative changes sign, it is called a point of inflection. Or what I call it is an IP, inflection point, IP. Okay?